Hi, welcome to this video. I'm just going to talk fairly briefly about the different specific heat capacity experiments on the Leaving Cert Physics course. So there's two experiments. We have to figure out the specific heat capacity of a solid and of a liquid. We'll start with the solid first because it's a little bit easier, and then we'll move on to the liquid one. So we have the diagram for the experiment here. Before we start talking about the diagram, let's just look at the formula for specific heat capacity. The most common one you're going to see is E is equal to mc delta theta. So if we're heating something up, the total heat energy we put in will be equal to the product means multiply these together, right? The mass of the thing we're heating up times the specific heat capacity times the change in temperature that we're heating it up by. So if we're going from 10 to 20 degrees, that would be a change in temperature of 10 degrees. Or if you go from 50 to 70, that will be a change in temperature of 20 degrees. So what I'm going to do here, first of all, is just rearrange this formula because we are trying to find specific heat capacity. So let's make C the subject of the formula. That means we're going to get C by itself in terms of everything else. So to do that and to get C by itself, we have to get rid of the m and delta theta on the right hand side. And if we're dividing the right hand side by m delta theta, we have to divide the left hand side by m delta theta. On the right hand side, these will cancel, and we'll just be left with C, our specific heat capacity. On the left hand side, we're going to be left with E divided by m, our mass, times the change in temperature. It's conventional to just write out C by itself on the left hand side, so I'll do that now, but it's mainly just for my own satisfaction. So basically, what this means is if we want to find the specific heat capacity of a solid, we need to measure the energy we use to heat it up. We need to measure its mass, and we need to measure the change in temperature as we heat it up with that energy. Then we'll fill that into this formula here, get the mass and get the energy and divide it by the mass multiplied by the change in temperature. So if we look at the diagram here, let's remember the three things that we need to measure are energy, mass, and the change in temperature. So if we can measure those three things, we should be able to figure out the specific heat capacity. So we have a block here that's usually aluminium or copper. We have a joule meter, which is going to supply electricity, and this will measure our energy that's going into the block. Before we start the experiment, we're going to use a mass balance, which is kind of a similar thing to a weighing scales, to find its mass. So we're measuring energy with the joule meter, mass with the mass balance. And then we need to measure change in temperature. So we have another hole in the block here that we put the thermometer into. We measure its start temperature, we measure its end temperature, and that will give us our results. So I'm just going to make up some results here. Let's say we put in 17,000 joules of energy. You can fill that in for E. Let's say the mass of the block is 1 kilogram, which it roughly was for us. And let's say the change in temperature is 10 degrees. So we might say it goes from, 25 to, or from 15 to 25 degrees. So that would be a change in temperature of 10 degrees. Again, to get that change in temperature, delta means change, theta means temperature. We just find the difference. So if we ended up at 25, started at 15, we just find the difference between those two numbers. So that would be 10 degrees Celsius is our change in temperature. And then we just calculate this out. So you could use your calculator for this part. It's going to be 17,000 on top. They look a bit like sixes, but they are zeros, I promise. And then at the bottom, 1 times 10 is 10. You can put that into your calculator. 17,000 divided by 10 is 1700, 1,700, right? So our unit then comes at the end, joules per kilogram Kelvin. Now, if we look at the second experiment for specific heat capacity, it's going to be the specific heat capacity of a liquid. So Honestly, the process is going to be pretty similar. If we look at the formula though, it's a little bit different. This time, because we're heating up water, the water has to be in a container, a copper calorimeter here. So we're not going to be able to just heat up water because there's a container that it's in. So we're going to have to heat up the water and also heat up the container. So if the water starts off at 10 degrees and we heat it up to 30, yes, we do need to supply enough energy to heat up the water to 30 degrees, but we also need to heat up the container to 30 degrees, otherwise the water won't be able to go to that temperature without bringing the container along with it. So we just have to be conscious of that in our calculation. So if we look at this formula here, the energy that goes in is going to be used to heat up the water. So the amount of energy needed to heat up the water will be mc delta theta for the water, because that's the amount of energy needed to heat up water. It depends on its mass, it depends on the water specific heat capacity and the change in temperature for the water. But we're also putting in energy to heat up the calorimeter. So that'll depend on the mass of the calorimeter, the specific heat capacity of the calorimeter, and how much the calorimeter's temperature is going to change by. Let's just rewrite this down here. The total energy that goes into this is going to be equal to the energy needed to heat up the water plus the energy needed to heat up the copper calorimeter. Okay. Now, if we want to make this formula a little bit more useful, we know that E is equal to mc delta theta. So for water, to calculate the energy needed to heat up the water, we can say it's going to be mc delta theta for the water. And for the calorimeter, the energy needed to heat that up will be mc delta theta for the calorimeter. And again, that's together going to be equal to the total energy we put into the system. So a little bit more values to fill in here. So one thing that we're going to do first of all is measure the mass of the calorimeter. Get a mass balance. Imagine that's a mass balance, and we put our calorimeter on top, and it'll give us a mass, right? It's going to give us the mass of the calorimeter. Then we can put a little bit of water in here, and we'll measure the mass again. And this time we won't just get the mass of the calorimeter, it's going to tell us the combined mass of the calorimeter plus water. So let's say that's 100 grams, and the mass of the calorimeter by itself was 20 grams. If we wanted to find the mass of the water then by itself, because we'll need to fill that into the formula, mass of the water, what we do is we just find the difference, right? So if the calorimeter with water in it is 100 grams, take away the mass of the calorimeter, and it'll leave you with just the mass of the water. So that's going to be 100, take away 20. These are just some sample numbers I'm picking out of my head. It's going to leave us with 80 grams of water, right? That would be the mass of the water. Okay. So that's how we measure our masses. So we'll be able to measure the mass of the water that way and the mass of the calorimeter. And we're only trying to measure in this experiment the specific heat capacity of a liquid. So we can say that we already know the specific heat capacity of the copper calorimeter already. And in an exam, it will be given to you in the question. So that's okay. We know that specific heat capacity there. And the change in temperature then will be fairly straightforward. So you measure the temperature at the beginning and the end. For the sake of simplicity, let's say again it starts off at 15 and it goes to 25. So we just find the change in temperature there by subtracting those two numbers. 25, take away 15, and 10 is a pretty easy number to work with, so I'm going to go for 10. Okay, that's 10 degrees Celsius, our change in temperature. So if the water heats up by 10 degrees, then the calorimeter will heat up by 10 degrees. And again, we're measuring that temperature change using a thermometer. All right, and then the final thing that we'll be able to measure is the total energy going in. Because again, any electricity you put in, we put it through this joule meter, so it measures that energy fairly accurately for us. Okay, so at this point now, we've got everything. We'll be able to measure everything apart from specific heat capacity of water. C, specific heat capacity, W for water. So that's going to be our only unknown. And if we have one unknown, then we'll be able to solve for that unknown if we can fill everything else in. So I'm going to try and pick some simple numbers just to make life easier. Let's say we measure the total energy that goes in as 10,000 joules. The mass of the water here we said is 80 grams. So to go from grams to kilograms, we divide by 1,000. It's going to be 0.08 kilograms. Specific heat capacity of water, we actually don't know that. Again, that's specifically what we're trying to figure out. The change in temperature for water, we already calculated as 10. Then over here, the mass of the copper calorimeter, we said was 20 grams. So again, if it's grams, we want to put it into kilograms before we fill it into our formula. So divide 20 grams by 1,000, you get 0.02 kilograms. Specific heat capacity of copper, they'll give you in the question, it's actually 390. And then the change in temperature is going to be the change as the change in temperature for the water there. And they both heat up by the same amount, which in my example with nice easy numbers is 10 degrees. So now if we multiply some of these out to simplify them, 10,000 on the left will stay the same. Over here on the right hand side, we can multiply our 0.08 by 10. So that's going to give us 0.8. And that's still multiplied by CW, right? These three things here, there's no sign in between them. So we multiply them by each other. 0.08 times 10 is 0.8. And then CW is unknown. The next three numbers there over here is 0.02 times 390 times 10. We multiply those by each other. You can use your calculator for that. And that will give us 78. Now to finally solve this equation, again we have one unknown variable here as CW. So we'll bring our unknown variables to the left hand side, keep the normal numbers on the right hand side. So this is going to go over to the left hand side. This is a normal number, so that's going to go over here. And 78 will just stay where it is on the right hand side of the equals. So when 0.08 moves to the left hand side of the equals, it moves to the other side, so it changes its sign. So we get 0.8 times CW, and it changes its sign to a minus. On the right hand side, 78 stays where it is, so it keeps its sign, and 10,000 moves over, so it becomes minus 10,000. On the left hand side now we have one term, on the right hand side there's two terms, so let's simplify those two on the right hand side. 78 minus 10,000, use your calculator for that. So your answer should be minus 9,922. On the right hand side we're still going to say minus 0.8 times specific heat capacity of water. Right now, all that we want to do is find actual CW. So to do that, we want to get rid of our minus 0.8 in front of it. The factor is minus 0.8 CW means it's minus 0.8 times CW. So the opposite of multiplying by minus 0.8 is dividing by minus 0.8. So let's divide both sides by minus 0.8. These will cancel on the left hand side, which was our plan, to give us 1 times CW. On the right hand side, 9922 divided by 0.8 gives us 12402.5. And a minus divided by a minus will give us a plus. Again, no, just do it in your calculator. Alright, now the last thing to do is add our units here. So it's specific heat capacity, so it's joules per kilogram Kelvin. There's our unit.